8.4 is on page 445, talks about equations with analytic coefficients. Given the standard differential equations, again, our whole theory, we're going to suppose that's a 1, always are forcing to be a 1, p of x, q of x equals 0, the traditional linear equation, the traditional differential equation. So theorem 5 says, suppose that x sub 0 is an arbitrary point of equation 1. Then one has two linearly independent analytic solutions of the form y equal series n equals 0 to infinity a sub n, x minus x naught, that point right there. Moreover, the radius of convergence, which is a crucial part of any power series of the form given in equation 2, is at least as large as the distance from this x naught to a singular point, real or complex. So the first set of problems, we want to figure out how big that radius is. Find the minimum value of the radius of convergence of the power series. Well, let's see. I look at this and I'm thinking, there's no singular points anywhere. If I run across from 2, then I should be able to run to infinity. That shouldn't be an issue. There's no restriction whatsoever. Versus if I look at number 4, on number 4, I'm going to make that a 1. Remember, that's going to be always our key. So I'm going to make this y double prime minus 3x over, that's x minus 3x minus 2, minus 1 over x minus 3x minus 2, y equal to 0. So here, we know there are two singular points, and the singular points are three, 2, and the point of interest is at 0. So in this case, well, how far can we go? We could travel as far as 2 units. I can't even hit the 2. So that's the biggest radius I can get. If I look at this problem, well, the same deal. The goal is to make that a 1. That is y double prime minus x over 1 plus x cubed, y prime plus 3x squared over 1 plus x cubed, y equal to 0. Now, this is a bit tricky because I want to figure out where this 1 plus x cubed equals 0. That's x plus 1 into x squared minus x plus 1, because they said real or complex. So I have x equal negative 1, and here I have x squared minus x. Take half of the middle number, which is 1/2, and square x minus 1/2 squared. That will be a negative 3/4. So x will equal 1/2 plus or minus radical 3i over 2. So here, I have to be a bit more careful, because if you remember how this plays, oops, wrong color. Okay, wrong color again. So, I have a singular point at negative 1, which is not an issue. That's easy. The point of interest is at 1. Okay, you know what? I'm going to enlarge those a bit. So I'm going to say this is negative 1. We have a singular point at negative 1, and we have it at 1/2. So if this is 3, 1/2 plus radical 3 over 2. We have a singular point right there. That is 1/2 plus radical 3 over 2. And 1/2 minus radical 3 over 2. This is the I part, right? And our point of interest happens to be at 1. So obviously I can't go that far. This is as far as I can go. So I need to know what this distance is. So if I really think about it, since this is 1/2 and this is 1/2, and up it's 1/2, it's radical 3/2. So this distance, which is the radius, that will be r squared equal radical 3/2 squared plus 1/2 squared. R squared will be 3/4 plus 1/4. R squared will be 1, so R will be 1. And that's as big of an R as I can get. And when we get to the actual solution, because now we're centering things at, so ideal to what we did before, but the work is a bit more intense. That's really how the solution should look like. To make this simple on what we want, we say, you know what, set it equal n equals 0 to infinity a sub n. Why don't you call this t, where you're letting x plus 1 equal to t, and at the end I'll replace it. So really x is t minus 1. So when I get to the equation here, I'm looking really at y prime minus 2 times t minus 1 y equals 0. I'll find the solution in terms of t based on what I already know. And at the end, I'll just replace t by x plus 1 and everybody is happy. So if I take a derivative of this, y prime is the series n equal 1 to infinity of n a sub n t to the n. So this will be the series n equal 1 to infinity n a sub n t to the n minus twice, when you multiply this, t times the series n equals 0 to infinity a sub n t to the n. This is n minus 1. Plus 2, the series n equals 0 to infinity a sub n t to the n equals 0. So now we follow on the traditional. What we want all of these powers to be the same. So we're going to shift this one up. Shift this one up. Shift this one up. To compensate, shift this one down. So that's our first order of business. This one I multiplied, it's going to be 2t to the n plus 1. So I need to make that t to the n. I'm going to shift this one down. Shift this one down. Shift this one up to compensate. And this one is already set. So the first order of business, like traditional, make those powers the same. They are. Now we need those to match. Oh, I didn't change that one. So we notice that this is n equal 1, which means we need to drop off a term right there. Let n equal 1. You get 1 a sub, n equals 0, I'm sorry. 1 a sub 1 plus the series n equals 0 to infinity. 1 to infinity, n plus 1 a sub n plus 1 t to the n. This is fine because it's starting at 1, so that is twice the series n equal 1 to infinity a sub n minus 1 t to the n. Here I'm going to drop off a term that is twice a sub 0 plus twice the series n equal 1 to infinity a sub n t to the n equals 0. So now I have a sub 1 plus 2a sub 0 plus the series n equal 1 to infinity. And I could run this up. That's n plus 1 a sub n plus 1 minus twice a sub n minus 1 plus twice a sub n. So here, for this to work, I need the constant terms to equal 0. So a sub 1 is negative twice a sub 0. Very good. And I have a sub n plus 1 equaling. So this is going to equal 0. Move that to the right hand side. That's going to be really 2 a sub n minus 1 minus twice a sub n. When I divide by n plus 1, there it is. That's a condition. And I need to list a few of these terms, not really that much. So a sub 1 I have, a sub 2 I have. So remember, I need a few terms. So if I let n equal 1, I'll get 2. that's twice a 1 in there, that's a sub 0 over 2 minus twice a sub 1 over 2. But I know what a sub 1 is. So this cancels out and this cancels out. That is a sub 0 minus a sub 1 is really negative twice a sub 0. So that's going to be 3a sub 0. So a sub 2 is 3a sub 0. And if I find maybe one more, if I want to find a sub 4, so you put 2 there, 3 there, a sub 2, a sub 3. If I want to find a sub 3, put a 2 there, that's twice a 2 in there, a sub 1 over 3 minus twice a sub 2 over 3. So that is 2 over 3. A sub 1 is negative 2 a sub 0. And a sub 2 is 3 a sub 0. So what is that? That's negative 4 over 3 a sub 0 minus 2 a sub 0. So that is altogether negative 368 over 3 a sub 0. So now I say, you know what? Y equal a sub 0 plus a sub 1 times t to the 1 plus a sub 2t squared plus a sub 3t cubed, and the list goes on. So that's going to be a sub 0 plus a sub 1. We got a sub 1 to be negative 2a sub 0. A sub 2, we got it to be 3a sub 0. And a sub 3, we got it to be negative 8 over 3 a sub 0, t to the 4th, and then it goes on. So y would be a sub 0 into 1 minus twice, and I'm going to replace t by what it equals. And we would do the replacement of t with, oh boy, by x plus 1. And that will make the series centered at x equal negative 1 plus 3 times x plus 1 squared minus 8/3 times x plus 1 cubed, and the list goes on. And that will be the solution to this first order differential equations. And the series here is no longer centered at 0, it's centered at x equals negative 1. So we're not going to get into that as much since we did that in section 8.1, 8.2, and 8.3. But this is just a feel of how this looks like. And that's the end of the section.